Work is defined as the force applied to an object times the distance over which that force is applied. The force that is plugged into this equation must be acting in the direction of displacement. If the force is not acting in the same direction as the displacement of the object, that force is not doing any work. The units for work are joules, which is abbreviated with a capital J, and work is a vector quantity, so things can do either positive or negative work. Unless the force being applied is equal in magnitude but directly opposite an opposing force, the work will change the speed of the object. Before we can do any calculations, we must determine whether the force is doing work or not. In our first diagram here, we have someone pushing a box to the right. The direction of force is to the right, and the box will move to the right as well. Since the force and the direction of motion are in the same direction, this force is doing work. In the second equation, we have someone holding a book bag. The direction of the force is upward. The person is keeping the book bag from falling down. However, the motion is to the right. Since the direction of force and the direction of motion are not the same, no work is being done by that force. In the third diagram, we have someone lifting a bag of groceries. The direction of the force is upward. The direction of the motion is upward. Since they're both the same, work is being done. In the last one, the force is being exerted upward. However, the motion, as the person is walking, is to the right. Therefore, there is no work being done by that force. Once we have determined whether work is being done or not, we can calculate the amount of work being done. Work is always equal to the force times the distance that it has moved. Now, if we look at this picture, it shows a 25 kilogram barbell that is being moved upward 2 meters. Keep in mind that kilogram is a unit of mass. Because they're moving this object upward, opposing gravity, the force that they are applying must be equal to the weight of the object. Well, weight is equal to mass times the acceleration due to gravity. So we're going to plug in 25 times 9.81 for the force, and then multiply that by 2 meters for the distance, and the final answer is 500 joules. Now, if the force and the distance are in exactly the same direction, we know that we can just plug in force into the equation. However, if the force is at an angle to the displacement, we need to look at the component of the force vector that is parallel to the displacement. So we'll take a right triangle and use trigonometry to figure out what that component of the force is. In this case, the angle for the force is shown is this angle here, theta, and the distance is along the horizontal, so we need the horizontal component of the force. Because of where the angle is shown here, that component is going to be the magnitude of F times the cosine of theta. Many times you'll see the work equation written as FD cosine theta for this reason. However, keep in mind that it matters which angle is given. So I like to not memorize which trig function is going to get plugged in there, and just remember you need to use trigonometry to find the component of the force that is parallel to the displacement. So here we have a picture showing a man pulling a girl in a wagon, and that wagon handle is at an angle to the distance that the wagon is moving. It's at a 30-degree angle, so since the wagon is moving horizontally, we need to find the horizontal component of the force. If we were to drop a perpendicular, we would have a right triangle right here, and the side that we're trying to find is the adjacent, so we are going to be doing cosine. So cosine of the angle, 30, is equal to the hypotenuse, is equal to the adjacent, the force doing work, divided by the hypotenuse, which in this case is 50. I plugged this in, and we end up with 43.30127019, etc. When I go to plug this into the force equation, or the work equation, work is equal to the force, the component of it that is doing work, times the distance. I keep that entire number, which I accidentally plugged in wrong here, 43.3012, etc., times the displacement, which is 30, and you end up with your final answer. This question is asking us to find the amount of work done by each of the forces shown on the free body diagram. The question says a 10 Newton force is applied to push a block across a frictionless surface for a displacement of 5 meters to the right. It shows us the normal force and the gravitational force. However, since displacement is to the right, the normal force and the gravitational force neither have a component that is parallel to the direction of motion. So we don't need to find any work done for those because they are not going to be doing any work. To find the work is force times displacement. The only force doing any work is the applied force, which we're plugging in as 10 newtons, times 5 meters for the displacement, which is equal to 50 joules. All right. Again, we have a 10 Newton force applied to push a block across a frictional surface at a constant speed for a displacement of 5 meters to the right. Again, since the displacement is to the right, the normal force and the gravitational force are not going to be doing any work. So we can find the force done by the applied force, the work done by the applied force, which would be the applied force, 10 newtons, times the displacement, which would be 5 meters, and we get 50 joules. However, friction is also going parallel to the direction of motion. However, the force is in the opposite direction of motion, so the force is really negative 10 times the displacement is 5, and I get negative 50 joules. So the applied force is doing 50 joules of work. The frictional force is doing negative 50 joules of work. So if we looked at the total amount of work being done on this object, we could add up all of the work values that we found, and we would find that 0 joules of work is actually being done. However, if you weren't asked for the individual works as well, you could just find the net force and multiply that by the displacement. Well, the net force is 0 because the negative frictional force and the positive applied force cancel each other out. So the net force is 0 times 5 meters will also give me 5 joules. So work is always equal to the component of force acting parallel to the direction of motion. It is a vector, so the direction does matter.